In this lecture, we're going to continue with the topic on wave transformations. Now let's try to find out the breaker height and also the breaker depth. Breaker height is the wave height just before the wave break, and breaker depth is the water depth where the wave break. So the approximation or estimation of breaker height and breaker depth are based on numerous coastal observation, so that we get a behavior which can be summarized in a chart. And now we are going to use the chart to try to predict where the wave is going to break, at what depth, and at what height, wave height, when the wave break. Now the method is actually quite straightforward. If we have the unreflected deep water wave height h0 prime and the beach slope m, which basically is the slope that we are usually familiar with. Sometimes in hydraulic we tend to use S0 to represent the slope. And let's say if we also have the wave period T, then the process of estimating the breaker height and the breaker depth goes like this. First, we calculate a dimensionless term h0 prime over gt squared. So we use the h0 prime and the t here. Once we get this value, we will use the chart to obtain the breaker height over the h0 prime ratio. And once we get this ratio, since we know what is h0 prime, we can calculate the breaker height. Once we have obtained the breaker height, we can calculate the dimensionless term hb over gt squared. hb is from here, t is again known from here. And after we get this value, we use the second chart to obtain the ratio of breaker depth over the breaker height. Since we already know the breaker height, so we can solve for breaker depth. Basically what it means now is that if we know the wave period and the deep water unreflected wave height, we will be able to predict the breaker height and also the breaker depth if we know the beach slope. These are shown in the next slides. This is the first chart to estimate the breaker height. We mentioned that we need to first calculate this dimensionless term, and what we want to read from the chart is the ratio of hb over h0 prime. So if we have this value, we will read to the correct slope curve. This different curve represents different beach slope. So from here we go to the curve depending on the beach slope, and we go across, we read the hb over h0 prime. You notice that in this chart it has been demarcated for different beach slope, from the lowest slope here 0.002 up to 0.1, and you notice that this region, the breaker type is spilling type, this region is the plunging type, this region is the surging type. This is the second chart. Once we obtain the breaker height, we can calculate this dimensionless term, and we are going to do the same thing. We're going to move up and choose the correct curve which represents the beach slope, and then we move across to read the ratio of dB over hb. We notice that we have the curve m equals 0 here, which is the limit, where this represents a horizontal beach slope, which basically is impossible. So this is a very gentle slope, and this is deeper slope up to 0.2, which means it's 1/5. This is very steep already. which means that the limiting condition is m equals 0, and for m equals 0, or if the beach is very flat, then the breaker depth is about 1.3 of the breaker height. dB over hb is 1.3. Over here, when m is equals to 0, dB over hb is 1.3 from the vertical axis. Of course, the real beach cannot be perfectly horizontal, so it is very unlikely that the breaker depth can be 1.3 of breaker height, but less. So as a rule of thumb, we normally assume that for a relatively mild beach slope, the breaker depth is about 1.1 of the breaker height. Here, this figure shows the deep water wave approaches the shoreline. It undergoes shoaling, so wavelength reduces, wave height increases, and eventually it begins to break in the breaker zone because the wave steepness exceeded the critical value. The breaking zone usually will have a lot of turbulence, and it dissipates the wave energy, so that after that the wave has less energy, but as it continues to propagate shoreward, the wavelength continues to reduce, and here the wave height has reduced because of the wave breaking process. It has less energy, and by the time it reaches the beach, the residual energy might allow it to still erode the beach, and the sediment may be carried up to the limit of this wave breaking zone, where the sediment may be deposited. We call this the longshore bar. Usually the longshore bar is located underneath the breaker. You notice that in fact the deposition zone here, the longshore bar here, is the location whereby the deep water wave approaches and break. The deep water doesn't go all the way directly to the beach usually, but the process is usually cyclic. That means if there's no longshore bar, then the wave can progress all the way to the beach. But because of the large amount of energy that it carries, so there will be erosion, and eventually the eroded material is carried shoreward and form a longshore bar here. Since the location of the longshore bar here is very shallow, so now the offshore deep water wave, when it moves towards the shoreline, then it breaks at the longshore bar instead of near to the beach. So if we stand at the beach here and we look at the wave breaking, then we can always make a intelligent guess that there will be a longshore bar beneath. And if we are able to guess the wave height by eye observation, then we also can tell roughly how deep that part is. So if the wave height is 1 meter, then the depth there will be maybe slightly more than 1 meter. And of course, in the beach area, it is most advisable not to swim beyond the breaker zone, not only because this part is dangerous due to the wave breaking, vigorous turbulence occurring, but beyond the breaker zone, the beach is likely to go deeper and deeper much faster. This slide shows the view of a person standing on the beach. You can see the rocks over here. You can see that very far away, there's no wave breaking, and the wave breaking occurs somewhere here along this line, so we can expect that that is the position where there is a longshore bar, and using our eye observation we can guess how high is the wave, so we can also guess how deep is the water there, and it's very likely that the water will go deeper here, then become slightly shallower right there, but it will become deeper further away from that point. Now let's try to look at this example and solve for the breaker height and the breaker depth. Follow the steps that is just explained. Earlier we have discussed about how wave height changes due to various wave transformation processes like shoaling, refraction, diffraction, reflection, and here we want to add that wave height also changes due to wind effect. In fact, we already mentioned before that wave is created due to storm or due to wind action on the sea surface. So wind is the primary agent that add or take away energy from the ocean or the coastal surface. Now, if we have an offshore directed wind, which means a wind that is moving towards the offshore, then it tends to retard, it tends to reduce the wave height, and so cause the wave to break at shallower water. Whereas if we have onshore wind, that means a wind that moves towards the shoreline, then it tends to add energy to the wave which is already moving towards the shoreline, so that the wave height may increase, and as a result we might get a spilling tide breaker. Previously we already discussed how to estimate the breaker height and the breaker depth, which is the point where the wave will break, and here we are going to look at plunge distance. When the wave has reached the breaking point, it will break over a distance instead of at one point. For example, as shown in this figure over here, where we have a plunging breaker, the plunging breaker will form and it will continue to move forward until it breaks, and that is a finite distance. So the distance can be estimated using this equation here. If we have a plane slopes with a slope of m, then we can estimate the plunging distance using this equation, which of course depends on the breaker height and also the wave steepness. And in case where we have a slope with submerged bar, the longshore bar, then we can use a very similar equation, and depends on the same set of parameter, but added with this constant 1.8 for us to predict the distance that it takes for the breaking to complete. So a longshore bar actually causes the plunge distance to be shorter.